Good afternoon, everyone. My name is Stephen Hollander. This week I am the lead for Group 2, talking about the gas turbine experiment. Start off, give you a little outline, talk about the introduction, some applications of gas engines, our objectives, what are we trying to obtain from this lab, some theory behind it, lead into some calculations, and ultimately end with some results and conclusions. As all of us know, jet engines are commonly used in the aviation industry, mainly due to their high thrust to weight ratio. This makes them ideal for propelling aircraft. Some fundamental components of jet engines are the nozzle, compressor, burner, turbine shaft, which we'll see later on in the presentation, and it's based off the Brayton cycle. Brayton cycle, it's a thermodynamic cycle, but the characteristic of it is that in the intermediate steps it has a constant pressure curve. So some of our objectives. The purpose of this experiment is to become familiar with operating thermodynamic principles of jet engines. Basically, we want to dissect the cycle and see different pressures and temperatures at the operating points. We want to do good housekeeping work in a sense. We want to record appropriate temperature and pressures, as well as thrust values, and ultimately determine the performance of the jet engine. So this is from the lab manual, the apparatus that we will hopefully be using. I'm not sure if it's actually will be working next week or not. But if you follow the white line here, that's the flow of the air. It goes through the compressor into the combustion chamber, and then the outputs over here. It turns the blade and out the converging nozzle. Note that at these intermediate steps, we're measuring the temperature and the pressure along the way. It's a little theory in general. It's basically taking the apparatus, breaking it down into a schematic sense. The air comes into the compressor, then goes to the combustor, mixes with fuel, goes through a chemical reaction, combusts, and goes through the turbine. The turbine is responsible for the output work, which is really in two parts. You have the internal work, which spins the main shaft, which ultimately kind of feeds back to the compressor, and you also have the true output work, which leads to your propulsion. This is a temperature entropy diagram for the Brayton cycle. Note that the solid lines are the ideal case, isentropic from 1 to 2, as well as from 3 to 5. For us, it's not the case, and we can't really get ideal necessarily. And so we're going to follow along these dotted lines. From 1 to 2, it's the compressor component, 2 to 3 combustor, 3 to 4 turbine, and 4 to 5 nozzle. It is a cycle, but it's an air-breathing jet engine, and so it's not reversible. It's also a good time to mention the efficiency. There's a couple different ways to measure efficiency. One of them is the pressure difference. These lines right here, the curve, are isobars, so constant pressure, and the higher difference or gradient in pressure you have is proportional to your efficiency. It gives you a larger work output. Another way to measure efficiency is through energy divided by the mass of your fuel, essentially. So we were asked in the lab manual to calculate or predict some calibration curves. And this first one is the fuel flow in gallons per hour versus the RPM of the engine. These data points were given to us in the manual, and I used a quadratic quadratic fit, and the correlation coefficient is about 99.3%, which is pretty good. But compared to this next graph of fuel flow versus the fuel meter, I was able to get a correlation coefficient of 99.96%. Again, using a quadratic calibration expression. So if I had to predict one or say which one do we use for calibration, I would say this one solely because it has a higher correlation coefficient. This diagram is plotting the predicted exit velocity versus the RPM of the engine. Note that there's a couple ways you can do this outlined in the lab manual, one of which is through continuity equation, mass flow. And that is represented by the blue line, where you could also use stagnation pressure formulas to get the red line. They're very similar, and also note that they're directly proportional to each other. These are some of the calculations that I used. Again, continuity is right up at the top. Mass flow is equal to rho VA. That was obtained in the previous graph, as you saw. The pressure gradient is right there. The pressure total is equal to the dynamic pressure plus the static pressure. Thrust is really equal to the exit velocity times the mass flow rate. And then, of course, you have, there was multiple fractions that we had to consider throughout the lab. I just put up the one for combustion to show you that it's the energy of during combustion over the energy of the fuel that you use. So in conclusion, based on those graphs, we found that RPM, mass flow rate, and exit velocity are all directly proportional. They all had, if one increased, so did the others. And this basically tells us, the faster we're spinning the engine through RPM, the more things we're sucking in, and of course, the faster you're going to spit it out. And also, higher pressure ratio increases the efficiency, assuming that all other quantities are held constant. So, thank you for your attention, and does anyone have any questions?